All right, welcome back, guys. In this lesson video here, we're gonna discuss the concept of differentials. And it turns out, this is as far as the math notation is a bit complicated, but the big picture or what it stands for or what we use it for. It turns out we use it quite often more than we know it in our daily life. So hopefully, at the end of this video, you kind of see that same thing as I'm seeing it, or you can ask questions on Zoom. So hopefully, the concept is clear before you do the homework. So before we get to the definitions and the notation for differentials, let's start with something that we already know from the previous lesson. So we know that the derivative of a function of a given, function f of x, we define that by definition is or as the limit as h go to 0, f of x plus h minus f of x over h. Okay. So h is literally just the difference between the two x values, right? So changing x in this case here, so that will give you h. Okay. So that was what we learned from previous lesson, the limit, the definition of derivative. So we're going to explore this a little bit further by introducing a few notation. So let's go ahead and define this here. Okay, so I'm going to go ahead and define. So let's go ahead and just define our definitions. So just notation. Let delta x, call this triangle with x, let that be the chain in the x coordinates or the endpoints of x here. So x plus h minus x. Okay, so let that be the delta x. What that's we delta x, also known as the increment. Let me spell that more clearly. So this can be as the increment. Okay, and then let's define our delta y to be the change in y. So f of x plus h minus f of x. Delta y is a change in y, delta x is a change in x. Delta x is also known as the increments. So if you're not familiar with these notation, this is kind of like, similar to the slope formula, right? So you got y2 minus y1, x2 minus x1, right? So think of this is your delta x, and then this is kind of like your delta y, sort of. Okay, but this is much more than just linear. This is for linear. So this what we have here. What we define here is the slope function for any function, not just lines. Okay, so let's apply this notation we got here. So let's go ahead and apply the notation which is introduced into this this limit definition here. So now we have f prime of x equal the limit of f of x. So now I'm gonna go ahead and change this into delta y, which is the numerator, the difference in numerator, and then delta x is gonna be your h here. So call that delta x there, because that's just x plus h minus x is gonna be h. And then instead of letting h go to 0, we're gonna have the limit as delta x go to 0, because our delta x is in this case equivalent to h. Okay, so by introducing the new notation here, we rewrite the definition of limit of the derivative in the limit form. So if the limit as delta x goes to 0 exists, if this exists, okay, then this is how we get the derivative here. Okay. So what's going to come next is kind of confusing here. Okay, so limit concept is we let some value tend to a certain number, in this case to 0. So we are letting the change in x very close to 0. So what we're doing here is let this delta x tend to 0, meaning this denominator here, let that value get really close to 0, get really, really, really small, and if the limit exists, then this limit, this left-hand side here, become the f prime of x, right? So from there, what we can say is, for extremely small values of delta x, because we let delta x tend to 0. So for extreme small value delta x, okay, call this formula here, call this formula there. So formula 2, that formula, okay, formula 2, we can say that now if we let delta x, suppose extremely small value delta x, then that formula there becomes this here, okay? Because the limit say, okay, as delta x goes to 0, this quotient, this delta y delta x, that limit will approaches a thing or expressions or equation, and that would be your derivative function, right? So suppose if we use small values of delta x, we can say it's going to be approximately close to the derivative, okay? So, and then from there, we can say, all right, well, if that's the case for small values delta x, we can even go further and say, well, that's going to be this here. The delta y is approximately f prime of x times the delta x. Let's rearrange that. Okay. All right. So this is true. Oh, this is true. Okay. This is true. This is saying that the change in the y values can be approximated by the derivative of the function at that particular value x times the increments of x. Okay, this is saying that for small increments, meaning small delta x increments, okay, the change in y, which is in this case change in y is delta x, can be approximated by the derivative at x times delta x. Okay. Now I'm going to draw you guys a picture. Hopefully with this picture it makes sense of what I just wrote in terms of the math there. So suppose I have a graph. Okay, and the graph looks like this. Okay, here's my f. Okay, and here is my x, and here is my f of x, and here is my x plus h. Okay, then up here is my f of x plus h. Then the increment, or the delta x, is this here, which is h. So that distance there is delta x. Okay. This tangent line here, the slope of this tangent line there, okay, that slope is going to be f prime of x. So the slope of that, so we say m is f prime of x at that point, okay, when you evaluate that slope tangent line. So we're saying that dy is this change in y. We're saying that this distance here, okay, that distance can be approximated, okay, by this line here, if we extend that, okay, right, f prime of x times delta x, meaning the slope of this, which is that thing, times delta x with this here, that will give you this here. Okay, so this distance here I'm gonna go ahead and highlight that. Maybe use orange. So this distance in orange here, that right there is our f prime of x times delta x. Okay, and that is using to approximate the delta y, which is the one in pink. Okay, that's hence why we have the approximation symbol. Okay, so you can see with small value of x, we can make this happen. So that what we call this thing here, right? That right there, we call that the differential. Okay, so f prime of x times delta x, we call that differentials, and we use that to approximate the change in y, the change in the function value. Okay, so let me go ahead and write down here as the formal definition. Okay. So differentials. Okay. We're saying that if y equal to f of x defines a functions, a differential function, then we define the differentials, the name differential, as the notation dy or df. So that's notation. Okay. By. Okay. So we define that as dy equal to f prime of x times dx, or df equal to f prime of x times dx, where dx is same thing as delta x. Okay. So from the definition of the derivative, we were able to come up with an approximation for the derivative using small increments, extremely small increments. And from there, we define, well, we kind of manipulate, we kind of manipulate this around and we get this formula. And we define the right-hand side, which is f prime of x times delta x, as differentials. Okay. So in other words, right. So differentials is the approximation of delta y, or change in y, by taking the derivative at that value at the current x value, times the increment, which is delta x. Okay. All right. So again, all this doesn't quite make sense yet. There's a lot of math, complicated, abstract stuff. When we do example, in terms of application, it's gonna make so much sense, and you're gonna start realizing that, oh, okay, well, I use differential all the time in real life. We may not think it as this complicated, but it turns out that it's a lot more simple than what I'm showing you guys here.